Welcome to EDU World Space.
All right, guys, we're doing problem number 76 of chapter 9 in chemistry essential. So they want us to explain the following. So first up, the peroxide ion, O2, 2-, has a longer bond length than superoxide ion. Then you can determine the validity of this by looking at the molecular orbital diagrams. So for O2, 2-, you fill up your sigma and pi orbitals, and then you also fill up both of your pi antibonding orbitals. Now, for O2 for superoxide, you're filling up your sigma and both your pi orbitals, but you're also filling up one anti-pi orbital, and then you're partially filling up the other anti-pi orbital. So remember, bonding orbitals, by definition, if you put electrons in these orbitals, they form bonds. They make your bond stronger. If you put electrons in your anti-bonding orbitals, because those are higher energy, that will weaken your bonding. So we can see that O2- has more electrons in anti-bonding orbitals than NO2. Peroxide has less electrons peroxide has more electrons in its pi antibonding orbital than superoxide does. And remember, the weaker your bond, the longer your bond will be. The stronger your bond, the shorter your bond will be. So the reason that peroxide has a longer bond length than superoxide is because peroxide has more electrons in its antibonding orbital, and that's what's causing it has more electrons in anti-bonding orbital, and that's what's causing the bond to weaken and the bond length to increase. Now, let's look at part B. The magnetic properties of B2 are consistent with if pi of 2p molecular orbitals being lower in energy than sigma of 2p molecular orbitals. So let me just write this. So this is so on the left we have sigma of 2p being lower in energy than pi of 2p. And over here we have pi of 2p being lower in energy than sigma of 2p. So we can actually look at the validity of this claim by looking at the molecular orbital diagrams. Now remember what paramagnetism is. Paramagnetism, you can know if a molecule is paramagnetic if it has unpaired electrons in its molecular bonding orbitals. Now, B2 is paramagnetic. So let's say we did the standard model where sigma of 2p is less than pi of 2p. So we can see that our electrons from our non-bonding orbitals would go into our sigma bonding orbital. They would be paired up. You would have no unpaired electrons. Now, conversely, if you had if pi of 2p was then your sigma 2p, you would have both your electrons go into your pi orbitals. And because your pi orbitals are degenerate, one electron will go in one orbital and one electron will go in the other. That will give you two unpaired electrons. So if you have two unpaired electrons, that means your sample is paramagnetic. So that means that we have a situation where this is the evidence for B2 being paramagnetic, and pi 2p is lower in energy than sigma 2p. So now let's go to part C. So the O2 2+ ion has a stronger OO bond than O2 itself. So we can draw the molecular orbital diagram. So we can see that O2 2+, we're filling our sigma and both our pi orbitals. Theoretically, this would have a triple bond, but that's not necessarily true in reality. Now, O2, you see that we have two more electrons in our O2 molecule than we have in O2 2+. So that means we filled up both our sigma and our pi orbitals, but now we're starting electrons in our anti-pi bonding orbitals. And because we're putting electrons in our anti-pi bonding orbitals, that's going to cause the bond in our O2 to weaken, and that's going to cause it to weaken and our bond length to decrease. So that's why the O2 2+ ion that has a stronger OO bond than O2 plus neutral, because as in the ion we don't have any electrons in our antibonding orbital that are weakening the bond between our oxygen atoms, but in O2 neutral O2 we have electrons in our antibonding orbital, and that's going to weaken the interactions we see. That's going to weaken the bond between our oxygen atoms. So to really understand these kind of problems, it's pretty simple. You have to understand the molecular orbitals, know how to use them, and be able to convert the electron configuration of your neutral atom into one you would see for a specific molecule, and know how to compare them. You also need to understand how bonding and antibonding orbitals work, and how electrons in your bonding and antibonding orbitals affect the strength of your bond, and also the length of your bond, because both of these are very important to help you understand this kind of problem. That's really all you need to know to solve this kind of problem. A theoretic O2 we know has a double bond, and theoretically O2 2+ would have a triple bond, so it would have and triple bonds are stronger than double bonds. So we know O2 2+ that would have a stronger bond than O2 neutral.